the instantaneous velocity and instantaneous speed. So when you are moving like this, so you know the average speed, you know the average velocity. What about somebody asks you that what is the speed here? So we saw the average velocity in any time interval. So there was a time interval from here to here. So this is okay, but if you are being asked that how fast it move at different instant of time, at particular instant of time during that time interval. So for that, let us suppose a particle is moving in some direction, one direction. The position is x and it goes for delta x. At x it was at t, and when it moves at delta x it was with delta t. So we get the average velocity of this particle at time interval delta t for the equation. We'll see about that. And we do not have the information about the velocity at different instant. We want that it has to be, because if you take time here, it is infinite time. This time, this time, this time, this time, infinite time is there. So during this time, the interval, the velocity of a particle, it might have increased, it might have decreased, but how to know this? We want smaller and smaller time interval. We want not this type of interval. We want very small interval. And as we go closer to a very short time, we get more and more information about the velocity at that time. So let us see the illustrations to actually understand what is going on. A car starts from rest, say at t equal to 0. It moves to a straight line, say in plus x direction. The velocity of car increases with time. Now a person who is sitting in the car, he takes reading and through speedometer at every second, and he notes them along the distance being traveled. And speedometer, as we know, indicates the speed of car at that instant. But our car moves only in one direction, so the speed and magnitude of the velocity will be same. So reading of speedometer comes in kilometer per hour, but we assume that it is in meter per second. So what are the tabulations, observation he has given? He took the readings like this. At 0, it was all 0. At 1, say 1 second, the displacement from the origin was 1.5, and the reading on the speedometer was 3. So in the same way at time 3, it was this displacement and this was the speedometer. Now suppose we start from here at t equal to 3. To calculate the velocity, we must know the displacement of the car, which is what? 13.5. And we must know the displacement of car, and for this displacement we need some time. So what will be the time, say from 3 to 6? The t1 is 3 and t2 is 6. So there is a difference of 3. So we say delta t is 3. We don't take this, but we say t plus delta t. So t1 plus delta 3, delta t is 3. So we reach at 6. So what will we do here is, delta t we start at 3 seconds. We said okay, the interval between, or the time interval is 3 seconds. We start with t equal to 3. We add this 3, that is t plus delta t. This is 3, this is 3, it becomes 6. In this time interval, the average velocity is displacement at 6 seconds, displacement at 3 seconds, divided by 6 minus 3. Of course, it will be 3 seconds. So what is the displacement at 6? See, displacement at 6 is 54. Displacement at 3 is 13.5. So when we take these values, 54 and 13.5, we subtract them, divide it by 3. We get some 13.5. But in the table, if you really go and see the value here, it is 9. At t equal to 3, it is 9. Reading of speedometer is 9. And what we are getting here is, we are getting 13.5. So it is way beyond the actual value which we have got. So in this calculation, for a time interval t equal to 3 seconds, the value of average velocity, it differs a lot from the true value. It has to be 9, but it came as 13.5. So we reduce now the time interval. It was 3, it was very large. So why not to make it the interval as 1? So in this interval, the value of the average velocity is 24.13.5. If you go back to the table, you will see, and the time is only 1 second. So it is 10.5. Now again, it is not closer to 9. So the car is moving according to the position. We assume that the position is given by 1.5 t square. Just assume this. Now, if this is the case, if x equal to 13.5 and x equal to say 14.415, this, if you put t equal to 3 here, you get this. But if you put t equal to 3.1 here, you get this value. Now let us calculate with this formula, you can say, or you can say the equation. Now we have taken the time interval as 0.1 second, 3 second and 3.1. So this interval 3.1 minus 3 is 0.1. And what is the What is the distance? 14.415 minus 13.5. So this is 9.15. So we have decreased the interval to 0.1 second, and we can again decrease the distance say to 0.05. Again we will use the same equation and we'll find out that the average velocity comes to be 9.07. Now this is much more closer to 9, which we wanted. So the idea is when we go on decreasing the time interval, when we made 3 seconds, 1 second, then when we move to 0.1, then 0.05. So we are decreasing, and the difference between the calculated value and the actual value is decreasing. Now the question will come, how much small time interval is sufficiently small? We cannot have a 0 value, but it should be infinitesimally small, which is near to 0, but it cannot be 0, because at 0 there will be no time interval. So why not to take limit? You know that limit delta t tends to 0 means it tends to 0, but it is not 0. It is very near to 0. So the circumstances in this scenario, two instant of time t and t plus delta t we will consider, and these are actually the same instant. That is t equal to 3 seconds and just near to 3 seconds. It is very closer to this, and we'll see that the value will come very closer to the observed value. So how to show it mathematically? Velocity will be delta x by delta t, that is x2 minus x1 by t2 minus t1. But here we are taking limit. So when we take limit delta t equal to tends to 0, then this delta x by delta t we know by mathematics that it becomes dx by dt. Dx by dt is the derivative, and you might have known when you learned the derivative, integrals, etc. Now dx by dt is called the derivative of x with respect to t, and what it gives you rate of change of position with time. Rate of change of position with time, and dx by dt is given by x dot above. What is instantaneous velocity from xt graph? Now here, say this one is the graph. Now you can take two positions p and q. You can join them and you can find the slope. But again, the distance t1, t2, the interval is large. So why not to take these 2 points? Again, you have distance is large. So by reaching here, at some point we'll reach as a tangent. This is a tangent. So we get a point which is just touching, but it is not 0. It is touching. So we want some delta t to tend to 0. So if we take this value, this line or this line, it will not worth. But if we take the tangent, then it will worth. So this tangent is simply delta x by delta t. Right? So this delta x by delta t, we just took some 3 seconds, now we took some 2 seconds, and now when we say delta t tends to 0, it is actually coinciding with the tangent, and this tangent is what we want. So now we have to note that for uniform motion, xt graph is a straight line, so that the value of instantaneous velocity is the same as the value of average velocity, right? And we are just talking about taking a tangent and finding the slope. So in instantaneous speed, here we'll just ignore instantaneous, we'll just call it as a speed. This is the magnitude of velocity. For instance, a velocity say plus 5.0 meter per second and velocity which is minus 5.0 meters per second, they both have a speed of 5.0 meter per second, because speed has no magnitude, no sign, only magnitude. So we have to take the magnitude of this. So speedometer of a car, it shows the instantaneous speed at that particular instant, and we have to note that though the average speed over infinite or say finite interval of time is greater or equal to magnitude of average velocity, the instantaneous speed at any instant is equal to the magnitude of instantaneous velocity at that instant, because we are taking the absolute values. Now the position of an object moving in one dimension is given by this equation. This is xt is equal to 4.2 t square plus 2.6. We have to calculate its average velocity in the time interval from 0 to 3, right? The instantaneous velocity at t equal to 3. So simply we know that x to the power n, differentiation of this is n x to the power n minus 1. We'll use this formula. Here xt is given by 4.2 t square plus 2.6. Now for t equal to 0 at this point, we'll put just 0 at this t, means here. So 4.2 into 0 square plus 2.6. The 2.6 is the initial position. When you take t equal to 3, that is here, t equal to 3, we get 4.2 into 3 square plus 2.6. This is the final position. And this is the final position, this is the initial position. we know that the average velocity is final position minus initial position, and the time interval is of course given as 3 minus 0. So it will be 12.6. How about finding the instantaneous velocity? We need to differentiate the position equation with respect to t. So dx by dt we have to do. So let us differentiate it. D by dt of this one, d by dt of this one. So d by dt of 4.2 t square is 4.2 will come out, t square is 2t. Here 2.6, because it is a constant, the differentiation will be 0. 4.2 into 2t, and we have to find t for t equal to 3. Put 2 equal to 3 and you get 25.2.